show some improved upper limits from comparing from the previous studies. So let me directly jump to the result. So CJD presented this data, this band 3 observation of band 3, which was carried out over this 250 megahertz bandwidth, and she presented this work. So I will briefly go to the data directly. So the data we analyzed had a bandwidth of 24 megahertz at the central frequency of 432.8 megahertz, which corresponds to the redshifted 21 centimeter signal from this redshift. And this was a high resolution data. It was observed over 4 nights, as mentioned previously. And for this particular work, I have restricted the baselines to 1 kilo lambda, where the density was found to be larger. And we are considering the combined nights data only, not the individual nights. Okay. So this is what we want to measure, the brightness temperature fluctuations, which can be written in terms of angular multipoles, and we cross-correlate these coefficients of the angular multipoles to estimate the multi-frequency angular power spectrum. We further use the ergodicity, that is the 21 centimeter signal is expected to be statistically homogeneous along the line of sight, and we use this quantity CL delta nu, where delta nu is the separation between these two frequencies as the multi-frequency angular power spectrum. So this is a flow chart of what I shall present. From the measured visibility, I shall use the tapered grid estimator to get maps, and from maps I shall estimate these quantities of interest, this cylindrical power spectrum, spherical beam power spectrum, and finally omega H1 BH1 through maximum likelihood estimators, which I shall present. So briefly talking about tapered grid estimator, so we use the measured visibility and convolve it with this function, which is the Fourier transform of a window function, which gives us this convolved grid visibilities. This can be visualized through this kind of grids, where this is the UV distribution at a particular frequency, and I'm gridding it to get the convolved gridded visibilities at a particular frequency. And this X here is two polarization states of the measurements, that is RR and LL. So in this particular work, I have first gridded the visibilities for RR and LL polarizations separately, and cross-correlated those two polarizations to estimate the multi-frequency angular power spectrum. Since the noise in these two gridded visibilities are uncorrelated because they are two different polarizations, so there is no noise bias in this estimator. Compared to the previous talks CJD presented, there we have combined these two visibilities to get the combined gridded visibilities, convolved gridded visibilities, and we correlated them and also subtracted the noise bias by subtracting the self-correlation of the visibilities which are coming from the same baselines. So we called it total correlation as compared to the cross correlation done in this work. So in this cross correlation, we are only considering the RR and LL cross correlation between these two polarizations, and in total we have both the self correlations RR cross RR, LL cross LL, as well as the cross correlation between the two polarizations. The idea is that we are getting, first of all, we are getting unbiased estimate, and second is that if there are some uncorrelated, if there is something, some systematics that are uncorrelated between two polarizations, we directly can avoid this through this cross correlation estimate. So here is the result. So in this blue curve, I have shown the multi-frequency angular power spectrum CL delta nu as a function of delta nu for a particular angular multiple L. There are many other angular multiples, but I am showing only one. And the blue one shows the estimates from total, and the yellow one shows what I got from the cross estimator. So the plot here shows DC subtracted value because the two had different DC levels, and it is easy for visual clarification. I am showing that. We see that there is an overall similarity between these two across the bandwidth, and this is mainly because of the foregrounds. And another thing is that we see there is a decorrelation from starting from delta equal to 0, the signal sharply falls. This decorrelation property is different in this cross estimator. We see that this sharply falls, but this slowly falls. this difference we find, and I shall describe this in the power spectrum also. What is the implication of this in the power spectrum? And the third thing we notice is that these blue curves have much the oscillations amplitude are much larger as compared to the yellow, where the oscillations are much smaller and pretty consistent with the noise which is shown in these dashed lines. So if now I consider the power spectrum, so the power spectrum is related to the multi-frequency angular power spectrum by a Fourier transform, where ANM this considers the Fourier coefficients, and this P, K parallel, K perpendicular, K parallel, these are the Fourier transforms. So these are the power spectrum. So we use this model, to model the measured CL delta nu, and we apply the maximum likelihood estimator to estimate the power spectrum. And this blue curve shows the power spectrum corresponding to the total estimator, and the yellow one is from the cross estimator. We see that because of this initial sharp decorrelation, the power spectrum, which is Fourier conjugate, we have a comparatively smoother than this yellow curve. This has higher power over a larger K parallel range, whereas this sharply decorrelates to noise level within this around 0.8 megaparsec inverse. And this blue line shows a theoretically predicted wedge boundary, which corresponds to foreground that is coming from the horizon. So this is the limit where foregrounds can go up to which K parallel. So we see that there is additional amount of leakage in this total correlation, which is not present in this cross estimator. And we speculate that this is probably has to do with calibration related error, which are uncorrelated between two polarizations, and in this cross estimator we can get rid of those effects. So here I have shown particularly one L beams, angular multipoles, which corresponds to 1 K perpendicular value. And in this plot, I am showing all of these L beams in a so-called heat map, which shows the cylindrical power spectrum over the all K possible, all available K perpendicular and K parallel modes. So we see that this is the theoretically predicted wedge boundary, which corresponds to the horizon, and we see that the most of the foregrounds, which are shown in red, are located inside the horizon, inside the wedge boundary, and there is some foreground leakage in these regions, which we avoided, and we saw it using this green dashed line, and we use this region, which we expect to be relatively foreground free, to constrain the 21 centimeter signal. So we use a maximum likelihood estimator for calculating the spherical beam. Usual way is to take these Fourier modes and take an average, which is a good estimator for a Gaussian distribution signal, or only when the signal is 21 centimeter signal. But in the presence of other systematical effects, that is not a robust. So and also at the same time, we impose the isotropy of the 21 centimeter signal by dividing the measured signal in these three terms. I shall explain one by one. The first term is the foregrounds, which we model using these modes, which we expect to be dominated by foregrounds. So this is this equation. And the second term is the 21 centimeter signal, which we model using these modes from the 21 centimeter window. And we divide this region into spherical beams and consider a constant power in each of the beams. So through this, we impose the isotropy of the signal, and this PKT is our parameter to be estimated, and this is how we define the chi-square. That is the measured signal minus the model. These two are the model, and the third one is the residual, which is expected to be considered with the noise. And this n is the noise covariance matrix, and these are the parameters that we estimate. And using those parameters, and we find the parameters pk from those in some k beams, and the results are shown in this orange line, sorry. And I have multiplied with k cube by 2 pi square to get the mean squared brightness temperature. And here I show the results from this cross analysis, and this total analysis that was presented in the last talk is shown here, and the analysis by Chakraborty is also presented here, which uses the delay spectrum based approach. And we see that the orange line is much lower than the total line, which shows that we have has an improvement in this results, and much of the improvements can be attributed to the systematical effect that is mitigated in the cross estimator, and also due to the less amount of foregrounds which we have checked when we consider the noise statistics, and we get and our results are quite similar to Chakraborty et al. Okay, and we find that most of the K-beams, these first three and the last three, are consistent with noise at 2 sigma level, and there are some foregrounds still there in some of these beams. Okay, so these are the upper limits that I'm quoting here. So at k equal to 0.8 megaparsec inverse, we have got delta square is equal to around 33 millikelvin square, with a noise which is close to the similar to the signal. We have an SNR of around 1, and the upper limit we get is around 59 millikelvin square, which corresponds to the upper limit on omega h on BH on to be 0.07, which we obtained from the dark matter power spectrum using this equation. This upper limit we can compare with the previous result that's shown by Sijaji, and this was he got this 130, and we got 134, around 134 megaparsec, which is around 5 times improvement. Okay, and this is comparable to the results obtained by Chakraborty et al. Okay, so we further wanted to improve our estimates of omega h1 and bh1, and we consider a foreground removal approach. So here we considered the fact that the 21 centimeter signal is expected to be like this. I mean, if you know the dark matter power spectrum, we can get an estimate of what the 21 centimeter signal will look like given a fiducial value of omega h1 and bh1. So the 21 centimeter signal starts with a high value and sharply decorrelates within 0.5 megahertz, around 0.5 or 1 megahertz, and then it has almost zero. So, but the foregrounds, as you can see, that foreground is almost correlated throughout the bandwidth. So this two decorrelation property allows us to separate foregrounds and the 21 centimeter signal. So we model the foregrounds from a region where the amplitude of the signal is much lower. I mean, the amplitude is fall around 90% from the initial value. So here we expect that the 21 centimeter signal is much less, but the foreground is there. So we use this region to model the foregrounds and extrapolate the model using the best fit parameters in this region to predict the foregrounds in this region. We subtract the okay, so I'll show the results. So here is one particular L that I'm showing, where the blue line shows the measured data, and this blue dashed line shows where I have modeled the foregrounds. So this region I have modeled for the foregrounds and extrapolated this curve in this region. So we subtract this blue line, these measured values, subtract the fitted data from the measured values, and these are the residual points, which are mostly consistent with the zero line, that is the noise line. So we can say that we have successfully removed foregrounds from this region and we have reached the noise level. These are the 2 sigma error bars. So we have done this for multiple L grids, multiple L values, and combined them together using a maximum likelihood estimator. And this is the limit we get. We use the baseline range within 1 kilo lambda, and the average L value is this for the L we have considered. And the omega h and bh1 value we get is around 0.88, so 8.8 into 10 to the minus 3, which is most, and we have the noise is much higher than the signal with an SNR of around 0.5, and the best upper limit we get is 2.2 into 10 to the minus 2. If we compare the upper limits with the present constraint from the quasar observations or many other observations that previously has been presented, so the upper limit, so omega h1 is expected to be around 0.10 to the minus 3 at these redshifts, and the linear bias parameter is around 1 or 2 at this redshift of 2.28. So we see that the upper limits are around 10 times larger. So remember, the foregrounds are around 10 to the power 4 to 5 times larger than the signal, but we are, I mean, very close and only limited by the noise. And this is 3 times better than the foreground avoidance results that I have shown before. So to summarize, we have cross-correlated the RR and LL polarizations, which gives us an unbiased estimator, and all the uncorrelated systematics, which are uncorrelated between 2 polarizations, are avoided in such a formalism. And also, if there are polarized foregrounds, such as polarization in the diffuse emissions or some other foreground, some polarization leakage or imperfect or calibration errors, these things we get rid of. And we have used the maximum likelihood estimator, which estimates the spherically beamed power spectrum directly from the maps, and it also incorporates the isotropy of the 21 centimeter signal. And we get an improved upper limits from that, which is around 59 millikelvin square, which is around 5 times better than our previous limits. And further improvements we get from removing the foregrounds using the polynomial fitting approach. And our upper limits are to 0.02, which is 10 times larger than the expected signal, but much better than the earlier intensity mapping constraints at this redshift. So I would like to conclude in a positive note that the future of the 20th centimeter cosmology is bright, even though we have brightest foregrounds. Thanks.
Okay, positive note. Okay, questions?
So, also question to Srijita. So you showed Srijita's results and your results together.
Yes.
Yeah. So the yellow line is from your cross correlation.
Yes.
And there you use maximum likelihood analysis.
Yes.
What about Srijita's results? You also use multiple maximum like.
So I will comment on that. So this particular approach of where we use the isotropy of the signal, this has not been used in the previous study. So in this study, that idea was not used. So in that work, we have averaged these beams. We have taken all the Fourier modes and averaged the power in this beam.
Yeah.
So the problem is that if there is some low values or some high values in one particular mode, suppose, so that will skew the average.
Yes.
Okay, it will make the average large or average low. So that thing is, so the maximum likelihood estimator is robust in the presence of outliers. So we get, even if there are some systematics, so we can be sure that the systematics will not affect our estimates. So that we have incorporated this here.
Yeah.
That is one thing. And the second thing is that we have used the cross correlation, for which we have got rid of many systematics that were present there.
Yeah, so for your cross correlation analysis, at the end you showed that your strength amplitude is around 10 to the minus 2 millikelvin square. So omega H value is around 10 to the minus 2, right? Or upper limit?
Upper limit.
Upper limit.
This.
So
okay, so this one.
Yeah. So
which one?
So you are saying it is an upper limit because you are not sure whether it's a signal or systematics, right?
So we say that if there were a signal, phenomenal signal, which has if it had an amplitude more than this, we could have detected.
But 21 centimeter signal could be of that order. I mean, of course.
No, the 21 centimeter signal is much below than this. Yeah, we are saying that we are dominated by.
But let's say you appraise the noise even further. So when do you say that now I have detected it? So that's the question.
Okay, so right now what we see finally that we are dominated by noise, and what we are getting basically is zero. We could have got negative also.
Yeah.
So what we are saying that we are dominated by noise now. So if we can go below the noise, we can get more observations.
Yes.
To get, to constrain better. We can get better constraint if we can lower the noise. Then only we can tell whether we have a significant direction or not.
Thank you.
Anyone else? Nirupam.
The way you are extrapolating into the smaller value, how much is that like model dependent in some way, the extrapolation part?
So
in the next,
yes. So we are not taking any other foreground models. We are modeling the foregrounds from the same data.
Right. But the extrapolation is done with some polynomial or
So this is modeled by a polynomial
yes.
which has these 10 terms where we have only considered the event terms because the CL delta nu is symmetric. So we have the best fitted values for those polynomials, and we use the best fitted values to extrapolate in the air this region.
So what sort of uncertainty will be on that extrapolated part, because
Yes.
that will propagate into your final inference from the
Yes.
residual on that part.
So for this method that we are considering, we have not considered the uncertainty in this modeling, in this fitting. For that, we have to do a Bayesian analysis, which we are trying to do using Gaussian process, but that we have not got any success yet. But here we do not consider the uncertainty of fitting here. And we have considered only those fitting for which the uncertainty is least. So we have an estimate of what can be the least uncertainty, which fits gives the least uncertainty. That estimate we have, but we have not incorporated that in the error bus. So the error bus will increase a little bit. Will increase somewhat depending on the uncertainty in this.
But that least, sorry, I'm probably we can talk later, but just last on this. So this least uncertainty that you are talking about is basically when you take the entire range and fit it with a 10th order polynomial.
No. This least uncertainty is only from this region. Because if I use higher order polynomial, this fitting will be better. But that can give us overfitting or underfitting. So we don't consider the least amount of fitting from there. We take a mean square error statistics in this region, and where the mean square error is minimized, we use that fit for ground removal.
Okay.
Anyone else? Okay, let's thank Asif again.